Okay, hello everyone. Thank you for joining on another uh, webinar session of the ISCB Student Council. Today, Edgar will give a presentation about uh, an accurate and efficient aligner method. He works in the Center for Genomic Regulation at Universidad Pompeu Fabra, and now he will start.
Thanks, Catalina. Welcome, everyone. Today, I want to present my PhD project. Its name is the Regressive algorithm. It's a new way to perform multi-sequence alignment. To start, what is MSA? What is a multi-sequence alignment? If we go to Wikipedia, all the PhD students or students in general goes, a multi-sequence alignment, as known as MSA, it's a sequence alignment of 3 or more biological sequences. At the end, if we are dealing with 3 or just a few sequences, we don't have any problems. But when data grows, the problem will appear. That's what is a MSA. Then for you could be like very strange topic or like not an important field to work with. But MSAs are used to phylogenetic reconstruction, mapping, or classification. And at the end, science is always numbers and citations. And if we go to the Nature top 100 papers cited, we can find that in the top 10, the number 10 is a Cluster W paper. It's one of the aligners most used widely, and that is what is MSA. Then the most used aligners is the progressive aligner. How it works? All the MSAs, all the aligners needs a guide tree. That it's the structure that we have here. Looks like a phylogenetic tree, but at the end, it's a clustering method, a clustering representation of how close are the sequence. These two sequences in this corner are closely related and are more closely related than this 10 and this one. As on this example, I will use these numbers as a length of the sequence. It's not important for the progressive, but yes, for the regressive, we will use it. How the progressive aligner works, like they start from the leaf, like from the bottom, aligning the most similar sequence, and they are going up until the root. The first step, they are aligning two sequence, like pairwise alignment, and then on the next step, it's going profile. It's taking the profile of 2 and 1, like the comparison, the 2 and 1 and the 6 and 4. This is a profile alignment instead of sequence until we reach the root, and this will be the result of a progressive aligner. All these profiles concatenated one after the other. Now that we have more or less an idea of what is a sequence aligner, I want to show you how the data is growing. When we submit the paper on the bioRxiv, December 2018, we were talking about the vertebrate genomes project. This project talks about trying to sequence 10,000 vertebrates, but to see how fast it grows, when the paper was accepted, just 1 year after, the community were already talking about the year biogenome project. We talk about 1.5 million species. Like we grow from 10,000 to 1.5 million just in 1 year. Then it means that the sequence aligners need to escalate as quick as data. That's it's not working. No, it's not worried. Just a small joke. That is scales up. No, it's not. Here on this plot, we can see like on the x-axis is the number of sequence, and in the y-axis the thesis score, a number that we evaluate how good or bad is the aligner. As you can see, when we increase the number of sequence, the accuracy grows as expected. Like if you have more information, in theory, your result will be better. But there is a barrier, a boundary around 1,000 sequence, where the aligners used to fall, will used to decrease the accuracy. It means that when they have more data, more information, there is a lot of noise and a lot of issues, and the accuracy starts degrading. Yes, I thought this was a message, but not. Then why they are so bad? Why the progressive are so bad? First, because the aligners, progressive aligners, and all of the other aligners, almost all of them, are based on profile alignments. It's what I told you at the beginning, that after the first step, we are aligning always profile and profile, and this increase the error rate. Large profiles, like the one at the top, is containing mostly gaps. Why? Because when the aligner make a mistake, introduce a gap that is not necessary, this gap is exponentially expanded through the root. And if we have one gap, we will have, at the end, we'll have 100 gaps just because this small error propagate the gap. What we said on the progressive is that once a gap, always a gap. You cannot fix the problems that you make before. And finally, in large columns, mutual information is lost. What that means? Here's an example. If we have this structure of 4 sequence, we have X and Y, like X and Y are always like, if we start with X, we finish with Y, and the other way around, if we start with Y, we finish with X. What's the result that we can have on a sequence alignment? We can get this result that is correct, like they're mutually exclusive, but the aligners nowadays allows to have these results. We can have X and X and Y and Y. This information is wrong. Like we don't have this information on the initial data, but because the aligners are heuristic, allows to get these results, and this produce a lot of misinformation. Then the potential fix, sorry, because I think that you are not seeing this image, but the slide will be online. There are just GIFs. It's not a big deal that you miss it. How we manage these issues, how we try to fix these problems. First, we try to reduce the number of gaps. How we do that? We avoid aligning large data sets. If we saw that after 1,000 sequence accuracy decrease, we just try to reduce the sequence up to 1,000. We just kind of make from the big MSA, we reduce and we make small groups of sub MSAs. Then to flattening, to avoid profile aligners, what we do is divide and conquer. It's the same strategy. From the big, instead of aligning big chunks of sequence, we just divide in a smaller, and we have a strategy of representative sequence that we will show on the example later. But at the end, we just divide a big problem in small pieces. And finally, to avoid ties, that we don't know which is the correct position of the nucleotide, we avoid early decisions. It means that we start with all the information. We start with from the most distantly related sequence. Like instead of starting from the bottom of the tree that we only know a piece of the puzzle, we start aligning from the bottom that are most distantly related, and we have a better overview of all the data set. That's the solution that we propose, the regressive algorithm. How it works? It's 4 steps. I'll go one by one. First, we label the intermediate nodes with the representative sequence. We go from the bottom to the top. That's an example. The same guide tree that we have before, and now these numbers, we will use it. This is the sequence, the length of the sequence. What we do is we label, like we put a value on all these nodes, okay? What we do is like we put the representative, we said. And at the end, we compare these two numbers and we push the longest one. Like between 2 and 1, which is longest? 2. Okay, we just push 2. What? It's the other way around. And between 2 and 6, we push 6. So far, so on, until we reach the root. Why we call it representative and why we took the longest? We took the longest because it works, and at the end because it's fast. It's an easy operation. We are not calculating the identity or something strange. Just the longest because we think that as long as the sequence, more information will carry. And why we call it representative? Because, for example, if we are here in this 11, we know that under this node, like all this sequence, the longest will be the 11. Like that will be the longest. The more representative will be this 11, and that's the first step. The second step, we collect n representative sequence from the root. We are going up, down now. N, we collect n sequence. In this example, we are using n equal 3, but on the real world, we use n equal 1000. Like you can play with different numbers, 500, 2000, depending of the liner, but for the article, we use 1000. It's kind of the best value that we can get. How it works? We want to have sub-MSAs of size n. We start from the root, from this 14, and we expand the tiles. Like we have this 11 and 14. These two tiles, it's a not, it's 3, no. Okay, then we go in the 11 and we expand the tiles, the 6 and the 11. Now we have three sequence. We have the 6, the 11, and the 14. We keep these 3 as the first sub-MSA, like the parent one, because it's the more high. Now we start with the 6, the same procedure. We span 2 and 6. It's not enough because we are looking for 3 sequence. We go in the 2 and we expand 2 and 1. Now we have 3. We have 2, 1, and 6. And we have like the first generation of the sub-MSAs. We go with the same level. We have everything like here. For example, we have 14, sorry. We expand, we have 13 and 14. We expand 13, we have 13, 12, and 14. We have these 3, okay? And finally, we go until we get we reach the leaf, like the ones that they don't have any children. Finally, with the 6, we expand. It only has 6 and 4, but there is nothing else, okay? We don't care, like we cannot do anything else. And at the end, we have all the, like from a data set of 1 million sequence, we have a lot of buckets, a lot of sub-MSAs of size n. And third, this is the only aligner step that we do. Like we align all the sub-MSAs with whatever aligner that we want. Like we start from this distribution. We have here, like in a list, on red is the sequence that is the representative, like, and it's common between generations. Like this 6 is the same of this 6, this 11 is the same of this one, and this 14 is the same of this. And here is the same. This 6 is this one, this 11 is this one, and this 13 is this 13. That's why we share a sequence that it will help on the next step. But once we have all the sub-MSAs, we can call any aligner. We have an image that we'll not see, don't worry. And at the end, we have a lot of sub-MSAs. We have the result, all the results. We have kind of a chunk of results. We can run this all in parallel because one is not depending on the other. Like instead of running one big job, we can run 1 million of small tiny jobs at the same time. And finally, we have to merge all these sub-MSAs of all of these results. We have to merge them at the end, have just one final result. How we do it? Thanks to the representative. Like as the example that we have 6, 11, and 14 in one generation, and in the other one we have 14, 13, and 12. Thanks to this 14 that is common in both generations, we can merge. How we do it? Here we are not aligning anything. We are just merging and expanding gaps. Like here is this PQ that here we have one gap and here we don't have any gap. Okay, we expand this blue gap on the purple sub-MSA. Okay, because here we didn't have any gap and here we have a gap. We expand the gap here. It's the same that here. And RS, we have one gap here but not here. Okay, we expand the purple gap in the blue sub-MSA. And if we have the same gaps, if we have gaps on both sides, like in this nucleotides and in these ones, because we can say that it's the same evolutionarity event, we have to stack. Like we just concatenate both gaps and we have the result. Like this will be the final result. We are merging with all the sub-MSAs, and at the end we will have this structure. But this is the 4 steps that I explain you one by one. That's nice, but I think that if you don't need to trust me, we have to check the numbers, and here are the numbers. On the first column, we have the aligner. Like we have math FFTNS1 aligner, cluster omega, up, math sparse score, and math GINS1. And then the guide tree, the clustering tree. We are using part tree from math and embed for cluster omega. And we are running this on HomeFam dataset. It's one of the datasets used for benchmark aligners. And this is the numbers on the top 20, like the datasets over 1,000 sequence. And we are measuring the TC score, total column score. On the non-regressive, like on the regular methods, we have these numbers, and we can see that on GINS1, math GINS-C is not able to run on over 10,000 sequence. And if we compare with the regressive, like with our numbers, we can see that we improve almost every time, and we are able to run GINS1, GINS-C on these huge data sets with a good accuracy. The good thing, or like one of the keys that I love this process, is that we are better than Cluster with Cluster. Like for example, here Cluster part 3, we increase almost 20 points without touching a line of code of Cluster. We are running Cluster like by default, but we are doing a pre-process of the data. We can say pre-process, but at the end it's on the fly, and we are kind of giving to Cluster the data in the way that he likes. Like if he cannot handle more than 2,000 sequence, okay, we just give them 1,000 sequence each time. And with a pure Cluster, we are able to increase 20 points accuracy, and we can run methods that were designed for small or tiny data sets, and they are very accurate because they have an algorithm that is very accurate, but it's CPU intensive and memory intensive. That's the numbers, and CPU time with in milliseconds. We have these numbers at the end used to be square, and with our method used to be linear. Like because we are not like we are splitting the problem and we are able to run in parallel, we are able to get this almost linear time. We have this kind of 7,000 milliseconds, but just because app it's doing pre-computation all the time, we're trying to see how we can handle or fix it or making a workaround. But at the end, it's not a problem. Like we can run up. The numbers are nice, and we are kind of we are faster. The same. We are faster than Cluster using Cluster. Like it's one of the beauties of this method. And to show how this difference between progressive and regressive, we have this plot here. On the x-axis is the CPU time, like on milliseconds, and on the y, the total column score. Okay, it means that if we go from left to right, we are going slower, and if we go up to the top, we increase the accuracy. Here on the blue square is the non-progressive methods, and if we go on regressive, we can see that almost all the times we increase accuracy and we are faster, or one of the two variables. For example, for Cluster part 3, we start here, and moving to regressive, we are able to increase the accuracy because we are going up, and we are going left, like we are faster, like we increase accuracy and time. For a sparse core and embed, we increase a bit the time, but we increase the accuracy. Like we are a bit slower, but we're able to increase the accuracy. And in this corner, we have the two GINS-C runs with different guide trees that we were not able to compare with a non-regressive way. As a conclusions, one of the points that I like, because I'm a computer scientist, I like because we're able to split the field. Like in the near future or now, we can split the teams. Like until now, all the teams that want to work on MSA, they have to work on the clustering method and the alignment method, because both things have to work together. With the regressive, we are able to have people focus on clustering methods, just how to compare the sequence and make the clustering be faster and more accurate. Another team just with alignment. They don't have to care about the clustering because Regressive can merge and combine all the methods. That's the next step, that we can combine any cluster and any aligner. We are almost linear in time. We are more accurate and more versatile because, as I show you, we can use methods that were coded in the 80s, that they were only prepared for a small 10 sequence or 20 sequence. And now we're able to run, like we just decrease n to 10 or 20, and we can run 1 million data sets with size n equal 20 with a software that was put in the 80s. And the take-home message or the take pandemia message, it is 4 steps. We are going, we label down up, we make the sub MSAs up down. We align only here, like we only have this aligner step. We only have one aligner step that can be parallelized. And finally, we merge everything together. I want to thank my teammates at CRG Barcelona. And here, more information, if you have any doubts, like you can contact me, but if not, you have the paper on the Nature Biotech, you have the T-Coffee documentation, and if you want to run and try on your dataset, you have this GitHub repository that it's an Xflow pipeline, that it's a workflow manager with a Docker container. It means that you can run whatever you want your analysis, that it's fine. And the slides, you can find the slides here. And that's all. Thanks for your time, and I'm open to questions, and I will try to answer.
Thank you so much for this talk. We will wait a few seconds to see if there are any questions. And meanwhile, I want to invite anyone interested in participating of the webinars to check the ISCB Student Council Twitter and Facebook to get information on when we open calls for abstracts and to see when other webinars will be given. I have a question because I understood that this is useful to use when you have a lot of sequences, but can it be used with long sequences? Does it have a limit on how long the sequences you want to align can be?
No, we don't find any issues on the length of the sequence. Like at the end, the length of the sequence, the only requirement that it has is just to ask for more RAM memory, because they have to store all the sequence on RAM. We don't store gaps in RAM. That's why memory efficiency we are better. But at the end, if you can, like, if your usual aligner works with a long sequence, you can plug on a regressive flavor and it will work. Like it's not an issue.
Okay, thank you. There don't seem to be any more questions.
Okay.
So yeah, we can end. Thank you so much for your
Perfect.
presentation.
Thanks for your time.
Bye.
Bye.